Hello, it's Keith here, and this is the second of the SuckHunt series of my Z80 programming tutorials. SuckHunt being the stereoscopic shooter I created just a few weeks ago. Now, the game is basically a Duck Hunt / Operation Wolf parody, but it's stereoscopic, which means if you've got 3D glasses, you can play the game in 3D. You've got some color code ones there, we've got some red cyan ones there, so you can play the game in 3D. And you can hopefully have some fun with it. Now, the game itself is a sort of railgun shooter. We have multiple weapons that you can pick up, like we can pick up that chibi gun there, and we can shoot the bats. It does support mouse, and it also supports light gun on the Sega Master System. This is a multi-platform game. It's currently only available for Z80, but basically we're going to be going over some of the multi-platform code today that makes this game tick, and hopefully it could be interesting to you if you're looking to create your own games, but you need to have some ideas on how to design the code in a way that's going to be efficient. Okay, well, we're going to go over to the source code and we're going to have a look at some of it today. Let's go over and take a look. Okay, so we're looking at the SH multi-platform code today, and we're going to start by looking at the random number generator and some of the other code that handles that kind of thing, and a few other little things as well. Now, the random number generator we're looking at today is the same one as it was used in YQuest, so it's not changed at all. It's exactly the same. The reason for that is it works. It's been tested. It produces random numbers from 0 to 255, so there's never any gaps in what it produces. They're sufficiently random for my purposes. So we're going to use it again. Now, it was designed for a game I was writing called Chibi Aliens, which needed 16-bit pseudo-random numbers that could be predicted and could be recreated from the same random seed, and that was the place it came from. Now, it creates a 16-bit number using two different routines, one for the high byte and one for the low byte. The low byte routine just uses some rotations and a few XORs and things to create a random number. The high byte actually uses some lookup tables as well, two 16-byte lookup tables. You can see there's one there and there's one there. So it's using two different ways, and this was so that there wasn't any noticeable pattern when the seed was incremented consecutively. It was a bit tricky to get a proper random number pair of bytes that looked completely unrelated from the same random seed. So that's why I was doing that. But actually, I don't think this game ever needs the 16-bit numbers. It only uses 8-bit numbers, which this function will convert the 16-bit numbers to an 8-bit number. So as I say, I'm not saying it's the best one at all. I'm sure it's not. It works. It's adequate for my purposes. And it's less trouble for me to keep using one that works than to try and create a better one, because you can end up with ones that don't produce certain numbers or have weird patterns in them. So that's what we're using. Now, a lot of times we will actually only want a random number within a specific range. And so to do this, we've got a command called doRangeDRandom. And this will take the B register and the C register, and it will use these as a range that will be a acceptable range that we will take. So B is the lowest part of the range and C will be the highest part. So if we want a value between 10 and 20, for example, we can set B and C accordingly, and that will just keep pulling random numbers until one is acceptable. That's what we're doing. Now we then extend this because we're going to often want to create new objects on the game screen within the logical units of the virtual screen. So we've got a virtual minimum X here, a virtual width, a virtual minimum Y, and a virtual height here. Now these are typically in pairs of pixels. So one logical unit is 2 pixels on the screen. Now in some cases these are converted to bytes for the actual visual representation, but as I say, the logical representation is in pairs of pixels because that's an easy way to make our X and Y coordinates work within a single byte, even if the screen is 320 pixels wide. So that's what we're doing here. We're using that doRangeDRandom to calculate the X and Y position, but you'll notice we're actually storing them in the register IY plus an offset. We're using that as the destination address. Now IY will point to the object that we want to initialize the X or Y position for. So if we wanted to make a new bat appear on the screen, we would point IY to the bat object. This OXPOS is a defined offset within the object definition. You can see all of the bytes of the object. Each object has 16 bytes defining its position and its movement and things, and the XPOS is byte 1 there. But we use those as a symbol definition here, just in case we need to reorganize the format later. But basically that will set object IY's X or Y position. Sometimes we want a fixed Y position but a random X position. Sometimes we want a fixed X position but a random Y position. So we've got those two to do that for us. We've then also got a routine here to handle the score. Now the score will appear at the bottom of the screen on the right. There's a bit of text that says score colon, and then there's the actual score. The score is stored in binary coded decimal. It's 8 digits, and this is packed format, and that means that there are 2 digits in each byte. If you don't know about binary coded decimal, I've got a tutorial on that. But basically, instead of each nibble storing 0 to F, each nibble only stores 0 to 9. So it's easier to show on the screen, but we need to use some different commands for the mathematics of it. So we're using locate XYZ, which is a 3-dimensional locate command, because our print string, our character drawing routines are 3-dimensional. So they take a Z pos as well as an X and Y. X and Y are in H and L, and the Z pos is in A. So we're setting the 3-dimensional position, showing the text string for the score. We're then setting the second line, which is going to be the actual score value, the 8 digits of the score, locating again, and we're using BCD show to show the 4 bytes of the score here. And the binary coded decimal routines are the same ones as in YQuest and in Grime, and I always use the same ones, so they work fine. So that's what we're doing. We've also got an apply score. This adds a score value to the current player score. This is for when the player has collected a power up or killed an enemy. We add some points. This is basically uses a definition of the score. So if you wanted to add 5 points, for example, we need a 4-byte value which represents 5, and then we add that to our score value, which is also 4 bytes. That's why we've got our byte definition here, and BCD add will do that. Again, the exact same function as last time, but we've got this refresh score here, which jumps back up here and updates the score. Now, where you can see we're running refresh score twice here, and there's a reason for this. Now, all of our drawing routines use XOR, and this means if we draw something to the same position twice, the second time we'll remove it from the screen. We're using XOR because this is easier to work with the 3D effect. But what it means is if we show the score to the screen in the same way as it's already shown, that will remove it, and then we show it again with the new score to show the updated score. If we didn't do this here, then we'd end up with an overlap score, and we'd end up with a splodgy mess, which we don't want. And then the other thing we've got here is a clear routine here. This will clear a sequence of bytes from memory address DE, and either we can clear them with zeros or we can clear them with an alternate value if required, although I don't think this game uses it. Some of my other ones have used non-zero values. The other thing we've got here is a range test routine, and this is to do with when the player fires at an enemy. Now, the enemy's coordinates are stored in memory as the center position, so when we're drawing a sprite, we have to calculate to the start and when we draw following from that. But when we shoot at the enemy, what we do is we take the position the player shot at, which is taken from the cursor position, we take the position of the enemy's center position, and then we take the size of the enemy as the range. Now, the only thing is the shotgun, which is weapon 1, has a special range. It has twice the range. Now, what we're doing here is we are getting the width and the height of the object here, and then what we need to do is to convert that into a range. And so what we're doing is we are taking that and we would halve it, but if the current gun is the shotgun, then we're actually going to double the range, and so we skip over that halving, and that will effectively double the range that we're checking here. The range is in H and L. We then take the position of the object in B and C here, and we've got the position that the player shot when this is executed in D and E. Now, at the start of this, of course, the object that we're comparing to is in IY, so there's a pointer to the object data in IY, and we're loading in the range checking values from that object here and setting the range according to the selected gun. Now, what we do next is we are actually testing, and we're comparing the object position with the range to the shot position. We're doing that for the Y coordinates and the X coordinates here, and if the object is within the range of the place that was shot, then we are setting the carry flag, otherwise we're clearing the carry flag here, and we will then test that later on outside of this routine. This routine will be run by the shooting routine, and then the shooting routine will act accordingly depending on the object that we've shot. Anyway, we're going to see that next time. That's all we're covering today. So if you've liked what you've seen, you can go to my website. SuckHunt is now available for download. It's available for the CPC, the Sam Coupe, the Spectrum Next, the MSX2, and also the Sega Master System. It's not available for all of the systems I covered, usually because it's such a complex game and a lot of those systems couldn't do the graphics, the stereoscopic effects I was trying to do. So those are the ones it's available for now. If you like that, please go and take a look. If you want to support my content, you can actually buy a SuckHunt t-shirt, which I'm wearing. They're available on my Teespring. Also now, I've actually written a book. It's in the last stages of proofreading at the moment, but by the time this is public on my YouTube channel, it will be available for purchase on Amazon. It looks like this. This is what it's going to look like, and it's 270 pages long, and it covers 5 different CPUs: Z80, 6502, 68000, 8086, and ARM. It's intended as an introduction for beginners. There's a introduction chapter which goes over all of the kind of terminology that you will come across in retro programming and in assembly, and I try and always explain everything in as simple as I can, down to earth ways with diagrams that will hopefully make it clearer for a relative beginner. Also, there is a section on each of the processors. There is an introduction to the processor, a description of how it works, the registers, the addressing modes, things like that. There are 3 examples on each processor, which is basically the same kind of content as the Simple series has done. And then there is a pretty full instruction set for that processor. Again, I've tried to describe all of the commands in a way that will hopefully be easier for a beginner to understand, rather than the crazy terminology that some of the processor manuals use, because some of those really made my head spin. So I've tried to explain them in ways that are simpler for a relatively normal user, rather than the crazy tech people who write processor manuals. Anyway, the book will be available. You can buy a physical print copy from Amazon, or you can get a Kindle copy. The price is going to be about $19 for the print copy and about $9 for the digital copy. So if that sounds interesting to you and you want to support my content, please have a look. There'll be the link below down in the description, so take a look at that. Anyway, I hope you've enjoyed this. I hope you'll have a go and get the SuckHunt code and at least play the game. Maybe you can have some fun with it. Thanks for watching today.